It is late. The glow of your monitor is probably the only light in the room right now.
Yeah, that classic late-night coding glow.
Exactly. You're a software engineer. Maybe, you're waiting on a build to finish, or maybe you're hunting down a memory leak that has just been dodging you for hours.
Or you're just taking a minute to reset before you dive back into your IDE.
Right. Wherever you are, welcome to the night shift. We have a really fascinating deep dive for you tonight. And, well, it starts with a paradox.
A pretty funny one, actually.
It is.
Yeah.
Have you ever wondered why a multi-billion-dollar AI, a model capable of passing the bar exam or, writing a functioning web app in literal seconds, why it cannot accurately count the R's in the word strawberry?
Right. It is the ultimate viral joke right now. People post these screenshots constantly to prove that artificial intelligence is, well, fundamentally stupid.
Yeah.
But what's actually happening there isn't a failure of intelligence at all. It's a structural artifact.
Mhm.
It's the result of the invisible layer of AI. And it's so foundational that if you don't understand it, the behavior of modern language models will seem completely, hopelessly irrational.
Exactly. So tonight, our mission is to decode that invisible first step. We are talking about tokenization.
The secret sauce.
Yes, the secret foundational layer where raw text is just stripped down and converted into numbers. Because, and this is wild to think about, when you are sitting there at your terminal testing an endpoint and you type "hello world" into an API prompt, the model does not see the letter H.
Yep.
It does not see the word world. It sees a sequence of integer IDs. It sees something like an array, like bracket 15496, comma 11, comma 995, comma 0, bracket.
Yeah, and those members are pulled from a fixed, hard-coded vocabulary dictionary. What's fascinating here is that, while developers are out there obsessing over parameter counts
Still.
or arguing on forums about who has the biggest context window, tokenization is arguably the absolute most critical design decision in building a language model.
The one nobody talks about.
Exactly. Before the attention mechanisms do anything, before a single neural network weight is multiplied, this one step dictates everything the model can and cannot do. It's the architectural bedrock.
So we need to understand how we actually arrived at this current architecture. And to understand why modern tokenization is so weird and honestly so complex, we first have to look at why the obvious simple methods completely fail.
Right, because they do fail. Spectacularly.
They really do. Because as a software engineer, if you tell me, hey, I need to turn text into numbers, my immediate instinct is to just go straight to the byte level.
Sure, character-level tokenization.
Exactly. Map every single letter to a number. I'd have a tiny, highly efficient dictionary, maybe 256 entries for raw bytes, or a few thousand if we just map out standard Unicode.
And, it seems perfectly logical from a systems design perspective. It's clean.
Super clean?
You'll never encounter an unknown state because your dictionary covers the entire alphabet. The model theoretically has access to every single atomic piece of data.
Right. But let's think about what that actually does to comprehension. It makes me think of trying to understand a massive, intricate Renaissance painting by examining it one single pixel at a time.
Oh, that's a great analogy.
Yeah, yes, you see absolutely every detail. You know the exact RGB value of every dot, but you completely lose the forest for the trees.
You have no idea what the painting is actually of.
Exactly. Take the phrase, understanding requires patience. In a normal human world, that's 3 logical concepts, 3 words.
Right.
But at the character level, you're forcing the machine to process a bloated sequence of 33 individual tokens, because every single letter and every single space is its own separate concept.
And that explosion in sequence length is where the hard math absolutely destroys the character level approach.
Okay, lay the math on me.
Well, we have to look at how a transformer model actually works under the hood.
Mm.
The computational cost of the attention mechanism scales quadratically with the sequence length.
Okay.
Yeah, that's a hard mathematical limitation of the architecture.
Yeah.
Every single token has to calculate its relationship to every other token in the sequence.
Wait, okay, let's unpack that for a second, because that quadratic scaling is the real killer here. If I have a 10-token sequence, that's roughly 100 attention calculations, right? 10 times 10.
Exactly. But if you switch to character-level tokens, your sequence for that exact same text is suddenly 4 to 5 times longer.
Oh, wow.
Yeah, so instead of 10 tokens, you have 40 tokens. 40 times 40 is 1,600 calculations.
Yeah.
You just took a 4x increase in data length and turned it into a 16x increase in compute cost.
That is brutal.
It is. And if you extrapolate that out to a typical document, your intention mechanisms are suddenly requiring exponentially more VRAM and processing power. It's just financially and computationally unviable.
Not to mention the conceptual hurdle, right? Because if you feed an AI one letter at a time, it has to implicitly learn how to spell before it can even begin to learn what a word means.
Yes, exactly.
Like, it sees C, then A, then T. Those individual letters don't carry any feline characteristics.
No, not at all.
The model has to learn from scratch that those three specific sequential integers represent a furry animal. It's like trying to teach someone advanced quantum physics, but first you require them to learn the alphabet.
Right.
Then how to read a basic sentence, then how to read a textbook, and only then can they get to the physics.
It's needlessly slow. It forces the neural network to use up millions of its parameters, just memorizing basic spelling and word boundaries.
Instead of learning actual reasoning.
Exactly, instead of world knowledge.
So if a character level basically bankrupts your compute budget and wastes your parameters, the pendulum naturally swings to the absolute opposite extreme.
Word-level tokenization.
Right. This is the other obvious approach. You just write a simple script to split the text by spaces and punctuation. The cat sat on the mat becomes exactly 6 tokens.
Which is great for compute.
Yeah, it keeps your sequences incredibly short.
But, and it's a big but it introduces a showstopper of a problem. It creates massive blind spots.
Okay, how so?
In natural language processing, this is known as the out-of-vocabulary problem, or OOV. Think about the sheer scale of human language.
Oh, it's huge.
Right. You have hundreds of thousands of common English words, then add tens of thousands of medical terms, add proper nouns, technical jargon, modern slang.
Compound words.
Yeah. If your dictionary tries to include every single word form, including plurals, past tenses, literally everything, you're looking at a vocabulary of maybe 1 million or more entries.
And 1 million entries in the vocabulary means your model's embedding table has 1 million rows.
Which is a nightmare.
For those visualizing the architecture right now, the embedding table is that massive matrix right at the input layer where each token ID gets converted into a dense vector of floating point numbers.
Right.
If your vector dimension is, say, 4096, and you have 1 million rows, man, you are burning gigabytes of incredibly expensive GPU memory just on the lookup table.
Before the actual brain of the model even starts working.
Exactly.
It becomes incredibly expensive in terms of memory. And there's a machine learning problem here, too.
What's that?
Well, rare words, say a specific medical term that only appears maybe a dozen times in your entire petabyte of training data, they'll have very poorly learned embeddings.
Oh, because there's just not enough context.
Exactly. The model hasn't seen them enough to understand what they mean, so engineers practically have to limit the vocabulary to save memory. They usually cap it at the 50,000 most common words.
But then, what happens when the model encounters something outside that top 50,000? Let's say it hits a rare medical term like pneumonal ultramicroscopic silicovolcanoconiosis. I think I got that right.
You did, actually. Impressive.
Okay, thank you.
But yeah, if the model hits a word like that, it just throws up its hands. It replaces that entire complex word with a single generic unknown token.
Just a blank.
Yeah. It's usually represented in the output as bracket, UNK bracket. All the specific, rich information contained in that medical term is instantly obliterated.
Oh, wow.
And because every single unknown word gets mapped to that exact same UNK token, the model can't even tell 2 different rare words apart.
That's awful. It's like having a dictionary that only works for words you already perfectly know.
Pretty much.
Like, if a user makes a typo, the model is completely helpless. Apple is a known token, but apple with 3 Ps becomes an unknown void.
Yes.
And this absolutely ruins performance for agglutinative languages.
Yes. Languages that build complex meaning by stringing multiple morphemes together into massive single words.
Like which ones?
Turkish, Hungarian, Finnish. Take this incredible Finnish word, Joksintillisenkohan.
Wait, what? Spell that out for me mentally. What?
Joksintillisenkohan. It's a single, perfectly valid word in Finnish. It roughly translates to, I wonder if I should run around aimlessly.
That is amazing.
It's a great language.
But I totally see the problem. A word-level dictionary could never realistically capture all the possible forms and combinations required for those languages.
No, it's impossible.
You'd need an infinite dictionary just to handle the variations of someone running around aimlessly. It's just an impossible edge case.
Exactly.
Okay, let's unpack this. We have 2 extremes that absolutely do not work. Character level bankrupts your compute with quadratic scaling.
Yep.
And word level creates massive informational blind spots and memory bloat. The industry had to invent a compromise.
And that leads us directly to the great breakthrough that powers almost every modern LLM.
Subword tokenization.
Yes, the Goldilocks solution.
Right, it truly is, because instead of forcing the model to swallow whole words or, starve on single letters, you break text into smaller, meaningful pieces.
Chunks of words.
Exactly. And the most common algorithm for this is called byte pair encoding, right, or BPE.
Yes, BPE.
Mm.
And the way BPE works is fascinating because it's completely data-driven. It doesn't use a linguistic dictionary to find syllables.
Oh, interesting.
It starts with single characters and just looks at a massive mountain of text. It sees that T and H appear next to each other all the time, so it merges them into a new token. Gotcha. Then it notices the and E appear together constantly, so it merges them into the. It just keeps iteratively merging the most frequent pairs until it hits whatever vocabulary size limit the engineer set.
Which results in this beautiful property called semantic compositionality.
Oh, I love semantic compositionality.
Right. Let's look at the word unhappiness. A subword tokenizer doesn't keep it as one massive, rare word.
Right.
And it doesn't break it into 11 individual letters. It logically splits it into 3 distinct chunks. An array of unhappy and smearoness.
And the model has already learned what un means from seeing thousands of other words like unhappy, unfair, undue.
It perfectly understands the concept of negation.
Exactly. It knows what happiness means from words like sadness or darkness. Even if the model has never seen the full exact word in its training data, it builds the meaning dynamically from the subwords.
I just love this because this is exactly how we read.
Yeah, it is.
Like, if I show you the word unflappableness, you have probably never seen that specific string of characters in a dictionary.
Definitely not.
But you don't freeze and throw in UNK error. You perfectly understand it.
Right.
You intuitively compose the known subwords, un, flap, summable, and fapenness. The model does the exact same thing.
It really gives you the best of both worlds. You eliminate the out-of-vocabulary problem completely because any novel word, any typo, any weird username can just be broken down into known subwords.
Well, that makes sense.
And in the absolute worst-case scenario, if you type absolute gibberish, the tokenizer just falls back to individual characters, which are always in its base dictionary.
That's brilliant, but designing the subword dictionary is a serious balancing act, right? You don't just pick a number out of a hat.
No, not at all. It is a highly delicate trade-off regarding vocabulary size. You're trying to find the mathematical sweet spot.
What happens if you get it wrong?
Well, if your vocabulary is too small, say only 1,000 tokens, every word gets chopped up into tiny pieces. We're back to the character level problem, where sequences get too long and attention compute spikes.
Okay, and if it's too big?
If your vocabulary is too massive, say 500,000 tokens, your embedding table is bloated, taking up too much VRAM. And worse, you actually lose that compositionality.
Wait, how do you lose it?
The model might memorize unhappy and unfair as entirely distinct, isolated tokens and never realize they share a fundamental negation prefix.
Oh, I see. It just memorizes them as whole shapes instead of related concepts. So the sweet spot typically lands between, 30,000 and 100,000 tokens.
Yeah, right in there.
GPT-4 sits at about 100,000. Llama uses 32,000. It brings to mind a fantastic currency analogy from our source material.
Oh, I like this one.
Character-level tokenization is like trying to buy a car using only pennies.
Good luck with that.
Right, you can technically do it, but carrying and counting millions of coins is a nightmare. Word-level tokenization is like trying to buy coffee with $1 million bill.
You just can't make exact change for the small, nuanced stuff.
Exactly. Subwords are the sensible denominations. They are the 1s, 5s, 10s, and 20s of language.
That is the perfect way to visualize it. You could handle any transaction, any sequence of text efficiently.
Now, understanding this sweet spot isn't just an academic computer science exercise. For you, the developer listening to this, the specific dictionary a model uses directly impacts your system architecture.
Absolutely.
And more importantly, your production API costs.
Yes, because different models literally see the exact same sentence differently.
Okay, let's look at a concrete example. The sentence is, tokenization is surprisingly important.
Oh.
Let's see how different models parse that exact string. GPT-2, an older model with a vocabulary of about 50,000 tokens, parses it into 6 tokens.
Yep.
It splits the capitalized word tokenization into 2 pieces, but it keeps surprisingly and important entirely intact as single tokens because they're common enough to have their own slots in its dictionary.
Right. But then look at a model like Llama, Llama chose a smaller, tighter vocabulary, 32,000 tokens.
Okay.
Because its dictionary has fewer slots, it has to split words more aggressively. It parses that exact same sentence into 7 tokens instead of 6.
Now, wait a minute. Let me push back on this. As a developer, compute is getting cheaper by the day. We have massive clusters of H100 GPUs.
Sure.
Does a slightly bloated sequence length really matter? If a llama takes 7 tokens instead of 6, does a, 15% increase in token count actually ruin my day?
If you are running an enterprise application at scale, yes, absolutely.
Real.
You have to consider the tokenizer when comparing models for a production environment. First, API providers charge you by the token, not by the word.
Oh, right.
If you use a model with a less efficient tokenizer, it inflates the exact same user prompt into more tokens. That directly, immediately increases your monthly API bill for the exact same transaction.
That adds up fast.
But it's also about your context window.
Right, the context window limitation.
Exactly. If you're building a retrieval augmented generation app, a RAG system, and you're stuffing 5 dense corporate documents into the prompt, an inefficient tokenizer might chew through your 8,000 token limit before you even fit the 5th document in.
Wow, you literally lose data.
Yes. A model with a larger vocabulary packs more actual text into fewer tokens, giving you a denser, more efficient context window.
That is wild to think about. Your system's memory capacity is totally dependent on how the model arbitrarily chunks the text. But wait, if I realize my tokenizer's inefficient, I can't just swap it out, can I?
Nope.
Like, I can't just plug the GPT-4 tokenizer into Llama.
No, you cannot. And this is a crucial concept. The tokenizer is an irreversible foundation.
Irreversible.
It is permanently fused to the model. Remember that embedding matrix we talked about?
Million-row nightmare.
Right. The model's input layer has exactly 1 row per token in the vocabulary. Every single weight, every single parameter in that massive neural network was trained to understand those specific text chunks.
So it's like pouring the concrete foundation of a skyscraper.
Yes.
Or committing to a primary key structure in a massive legacy database.
Exactly. If you decide you want to change the tokenizer to be more efficient, you invalidate the entire embedding table. You have to throw the whole multi-million-dollar model out and retrain it from scratch.
Man.
You can fine-tune the behavior, you can change the system prompts, but you cannot change the foundation once it is poured.
Which brings us to perhaps the most entertaining and frustrating part of our deep dive.
Bugs.
The bugs. These arbitrary token splits, these foundational concrete blocks, don't just affect your API bill. They are the direct hidden cause of the most viral, embarrassing bugs developers encounter when building AI apps.
Yep.
It's what creates that stupid AI illusion we talked about at the top of the show.
When you see a language model failing at a seemingly simple task, and people attribute it to a lack of reasoning, it is almost always a tokenization artifact.
Let's go back to the strawberry bug.
Let's do it.
You ask an incredibly advanced LLM to count the R's in the word strawberry, and it confidently tells you there are 2. People laugh, but let's actually visualize what is happening. The model literally does not see individual letters.
Exactly. The tokenizer sees the string strawberry and splits it into an array of 2 tokens, straw and berry. To the model, it is just processing ID 1493 and ID 4820.
Yeah.
It has to somehow deduce that chunk. A physically represents 5 letters, and chunk B physically represents 5 letters, and then perform a mental search for the letter R across a visual representation it doesn't actually have.
It's like asking a human who natively reads Chinese to count the individual pen strokes of a character in their head without writing it out on paper.
That's a great way to put it.
They instantly know the meaning of the character, but decomposing it into its atomic mechanical parts is a totally different, highly unnatural skill.
And we see this breakdown everywhere. Ask a standard model to reverse the word hello.
It should just be OLO.
Right. But if hello is stored as a single indivisible token chunk, the model has no explicit access to the letters ALO.
Let's try to visualize that. It's like if I asked you to recite a phone number backward, but you only ever memorized it as an auditory rhythm.
Right.
You didn't memorize the digits, you memorized the song of the numbers. To reverse it, you have to actively fight your own mental representation.
Exactly.
Yeah.
Even simple math breaks down this way. You ask the model, What is 124 plus 5678? That seems trivial.
Super trivial.
But the tokenizer might arbitrarily split those numbers into weird chunks based on frequency. It might see an array of 123 and 4 plus 56 and 78.
Imagine trying to do mental math when one person hands you the concept of 123 and 4 and you have to align it with 56 and 78.
It's a mess.
The digits are not neatly aligned in columns like they are for a human doing addition on paper. The model has to mentally reassemble those strained fragments before it can even attempt the arithmetic.
But there's another layer to this tokenization architecture, beyond just failing at math or spelling. And it's a massive structural inefficiency regarding multilingual text.
Right. This is a huge pain point for global developers. Tokenizers are overwhelmingly trained on English data.
Unfortunately, yes.
Because of that, common English words zip right through the system as highly efficient, single tokens. But if you input text in Hindi or a non-Latin script like Chinese, the tokenizer suddenly struggles to find matches.
A single Chinese character that represents a complete, distinct concept might not be in the vocabulary. So the tokenizer falls back, aggressively chopping it into 5 or 6 underlying byte-level tokens.
It's an incredible structural disadvantage baked right into the foundation.
Yeah.
Think of the context window like a massive multi-lane highway. The tokenizer system was built specifically for cars representing English words. The cars zip right through perfectly. But Chinese or Hindi words are treated like massive, oversized transport trucks.
Yeah.
They take up 5 or 6 lanes, they move slower, and they cause massive traffic jams in the context window. But not because the trucks are inherently slower. They are slower entirely because the infrastructure was not designed to accommodate them.
And the practical result for a developer building an app for an international audience is that non-English text eats up your context window much faster.
Wow.
It takes significantly more GPU compute to process the exact same amount of semantic meaning. And your API bill is fundamentally higher, simply because of the language distribution and the training data of the dictionary.
That is just wild. So as we wrap up this deep dive, the core takeaway for you, the engineer building these systems, is this. Tokens, not words and not characters, are the fundamental atoms of an LLM's thought process.
Yep.
Everything we talk about in AI, the attention heads, the neural pathways, the context windows, it all operates purely on these integer IDs.
That is the crucial shift in perspective. When you say a model has an 8,000 token context window, it is not 8,000 words.
Right.
And when the model predicts the next step, it is not predicting the next word. It is mathematically predicting the next token ID from its specific hard-coded dictionary.
And there are even invisible structural elements in that dictionary that you never see. Things like the beginning of sequence token, the padding token, the end of sequence token.
Embedded tokens.
Yeah. These invisible scaffolding elements give the model its entire structure behind the scenes, telling it when to start generating and when to stop.
If we pull back and look at the broader implication of all this, well, it leaves us with a rather profound question about the nature of machine intelligence.
Okay, hit me.
If a model's entire ability to, quote-unquote, think and process the world is strictly bounded by the arbitrary text chunks in his tokenizer's dictionary,
Right.
what human concepts or cultural nuances might artificial intelligence be structurally incapable of grasping, simply because it lacks the exact right subword to hold the thought?
Oh, wow. That is something to keep you awake tonight. You are not just dealing with code and APIs, you are dealing with an architecture that fundamentally dictates the boundaries of machine thought.
Pretty heavy for a night shift.
From the first pixel of text to the final generated response, it all starts in the dark with a simple integer. Good luck with the rest of your night shift and happy coding.